Swayam Prabha. Digital India. Educated India.
Welcome friends to this NPTEL course of environmental soil chemistry, and today is the fourth lecture of third week, and in this week we are actually discussing about the chemistry of soil organic matter, and today we are going to talk about the molecular structure of soil organic matter. Then we will be talking about the metal and soil organic matter complexes, complex of soil organic matter and clay, and how soil organic matter can bind different other pesticides and so on and so forth. So, today we will be starting with the molecular structure of soil organic matter. Remember, the basic backbone structure of soil organic matter is still an enigma. There are a couple of reasons that there has been so many confusion that there has been no clear definition of the structure of soil organic matter. And the structure of the soil organic matter comprises of similar functional groups and presence of aliphatics and aromatic compounds. So, you can see the presence of both aliphatic compounds as well as aromatic compounds. Now, using the 13C NMR study, soil was found to have paraffinic carbon and then methoxycarbon, amino acid carbon and carbon in carbohydrates and aliphatic structures containing aliphatic structure containing the hydroxyl groups, then aromatic carbon, then phenolic carbon and carbon in other groups. So, the carbohydrates, then proteinaceous materials like amino acids, peptides and proteins, and lipids like alkanes, alkenes, saturated and unsaturated fatty acids, alkyl, mono, di and triesters in soil organic matter are tightly bound by the aromatic soil organic matter compound. So, this is the the molecular structure of soil organic matter proposed by the scientists Schulten and Schnitzer in 1993, and it is basically a 2D structure, as you can see, where different types of aromatic rings, as you can see, these are different types of aromatic rings. These are different aromatic rings which are basically linked covalently by aliphatic chains. As you can see, different aliphatic chains are there which are joined basically through covalent bonds. So, this is a very complex structure, as you can see, and so in this structure one thing is clear, that oxygen is present as carboxyl. As you can see, the oxygen here is presence as carboxyl, and then phenolic, as you can see, the phenolic groups are also present, and then alcoholic hydroxyls are there, then esters are there, ethers are there and ketones. So, all these different groups are present, and nitrogen is present as heterocyclic structures and nitrile. As you can see, these are different heterocyclic structures, and the nitriles you can see here. So, the nitrile group and heterocyclic structures are also present, and the elemental composition is basically this 308 8, then H 328 O19 N5, and molecular weight basically they have calculated is 5.540 Dalton. So, the carbon skeleton which we are seeing has microporosity with voids which can bind various like various molecules like carbohydrates and proteinaceous materials, and not only the organic molecules but also different inorganic components like clay minerals and metal oxides. So, and water also. So, this is the kind of a structure, complex structure, and using different types of covalently bond aliphatic and aromatic ring, and then they are having some micropores where they can fix different types of inorganic, organic as well as water compounds. So, let us see other structures. So, Schulten and Schnitzer in 1993 they have proposed this structure. They have proposed another structure of humic acid. Now, in this humic acid structure, one molecule weight of humic acid was assumed to interact with 10% carbohydrates and 10% proteinaceous materials, and they proposed the elemental composition as C342, then H388, O124 and N12, and they have calculated the molecular weight of 6651 Dalton. And elementary analysis of that humic acid, they have found that it contains 61.8% of carbon, then 5.9% of hydrogen, 29.8% of oxygen and only 2.5% of nitrogen. So, these are some molecular structure given by different scientists group. And also Schnitzer in 2000 he has proposed a 3D structure of a soil particle, assuming that the soil has 3% soil organic matter and and 3% water and 91% inorganic components. So, as you can see, this is basically 3D structure, and we can see the soil organic matter and then triose, silica sheets and hexapeptides also are there. So, the basic elements they have seen, he has proposed that it is carbon, which is basically denoted by blue blue circles, then hydrogens are basically denoted by these white circles, then nitrogens are shown by these dark cycles, dark blue. As you can see, these are the dark blue circles. Oxygen, basically these are red, then silicon are purple, as you can see purple are there, iron is green and aluminum is basically light yellow. So, they have shown in this 3D structure different elements and how they are bound together to form this 3D structure of soil organic matter. So, if we see the molecular structure of soil organic matter, then voids in this model structure may contain different, as I have already told you that it can contain both organics, inorganics and water. Now, the functional groups would react with metal and inorganic material. We will see how they are interacting with the metals and inorganic materials when we will discuss the chelates. Now, they also provide nutrients to the plants and microbes by the process of chelation, which we are going to discuss. You will see that how they are providing the nutrients to the plants as well as microbes. The soil organic matter is bound to silicates by iron and aluminum ions. As you know that the silicates, we have already discussed in our week 2 lectures that soil contains iron and aluminum oxides. Not only that, iron and aluminum is also present in the clay mineral structure. So, soil organic matter can be bound in this clay mineral structure, and that is why the soil organic matter can coexist with clay minerals, and it is surrounded by a model of matrix of silica sheets. So, we will see in details of how they are joining together by the by a model of matrix of silica sheets while we discuss the structure in details. Now, the main reason I told you at the beginning of this lecture that the main reason that the basic structure of humus is still not fully understood, because there are 3 reasons. First of all, the humus structures are very heterogeneous and complex. Second, there are no regularly repeating structure unit or set of units. Just like in case of clay minerals, we know that in case of crystalline clay minerals like kaolinite, like montmorillonite, they have some repeating well defined structure. However, in case of humus, there is no repeating well defined structure, and that is why there is no 2 humic substance or humic molecules have the similar structure. As a result of that, their molecular structure is still not well described. So, if we see the macromolecular structure of soil organic matter. So, what is the macromolecular structure of soil organic matter? Macromolecular structure of soil organic matter basically shows its size and shape. So, the macromolecular structure is important as it affects the chemistry of soil organic matter and mineral complexes and stability of organic mineral aggregates and their fate transport of pollutants and carbon cycle in the soil. So, the macromolecular structure which we are going to discuss are basically affected by several parameters. First of all is pH, second is electrolyte concentration, third is ionic strength, and fourth one is humic acid and fulvic acid concentration. We will just see that how by changing these 4 different factors we can see different types of macromolecular structure. Sometime we will see some fibrous structure, sometime we will see some some round and some round some round structures and cluster structures. So, let us see how they will look like. So, basically in 1976 these two scientists called Chen and Schnitzer, they used electron microscopy to study the macromolecular structure of fulvic acid as a function of pH. So, these are different pictures they have taken at different pH level. So, let us see how pH can differentiate or how pH can produce different macromolecular structure of soil organic matter. Now, at pH 2, as you can see at pH 2, the elongated fibers and bundles are present. As you can see, this is showing elongated structures and bundles, and fibers were curved or linear. Now, at pH 4, the fibers were thinner and fiber bundles were more prevalent. As you can see, the fibers are thinner as and their bundles are more prevalent. At pH 6, as we increase the pH further, there was less and thinner fibers and more bundles and closely knit fibers. As you can see, there are more more bundles and closely knit. As you can see, the fibers are closely knit together. At pH 7, when we are further increasing the pH, a fine network of tightly meshed fibers were present. As you can see, a fine network of tightly meshed fibers, as you can see. At pH 8, further you are increasing the pH, the fine network has changed into a sheet like structure. As you can see, we are getting a kind of sheet like structure. So, we started with the thin fibers and then we are getting into the sheet like structure. At pH 9, that means highly alkaline condition, you can see the sheets are getting thicker, and finally at pH 10, which is shown by this picture, at pH 10 homogeneous grain like particles were present. As you can see, this is a homogeneous grain like particles you can see in this electron microscopic view of the soil organic matter. So, this is how the changes of pH basically determines the macromolecular structure of soil organic matter. Now, Ghosh and Schnitzer in 1980 used viscosity surface pressure measurement to study the macromolecular structures of humic acid and fulvic acid, and we have seen that these are some of the primary conditions based on which the macromolecular structures of different humic acid and fulvic acid molecules basically change. As you can see, in case of condition 1, let us consider condition 1. So, in the condition 1, when the sample concentration is high, which is greater than 3.5 to 5 gram per liter, and the pH is low, and simultaneously electrolyte concentration is high, which is 0.05 and molar and higher. So, if these 3 conditions are met, you can see that rigid and unchanged spheroids are present in the macromolecular structure. However, when the sample concentration is low and pH is quite high, which is greater than 6.5, and electrolyte concentration is low, then we will get a kind of flexible linear polyelectrolyte structure. So, as you can see, based on the sample concentration, pH and electrolyte concentration, as we have discussed, the structure of humic acid and fulvic acids are changing. This thing will be more clear when I will show you in the next slide. If you go to the next slide, you will see that basically what I have told you in the last slide, that in the sample concentration you can see there are 2 types of sample concentration. One is low sample concentration, another is high sample concentration. So, in this case we are talking about fulvic acid, and this is the chart of humic acid. So, low concentration and high concentration. So, in case of low concentration, when the electrolyte concentration in molar electrolyte concentration is basically low, we can see basically linear structures. However, as the electrolyte concentration is increasing, we are getting different types of spheroidic structure. However, when the concentration of the sample is increasing, we are getting spheroid like structures, macromolecular structures. Similarly, in case of pH, when it is low, we are getting spheroid structures. However, when we are increasing the pH, we are getting more thinner fibrous structures. Similarly, in case of high concentration also, for lower pH values we are getting more cluster, spherical structures. However, the fibrous structures are visible at higher pH. Similarly, in case of humic acid also, at low electrolyte concentration and low concentration of sample, we are getting the fibrous like structure. However, at higher electrolyte concentration like sodium chloride, we are getting spherical structures, and in case of pH, higher pH, we are getting, just like in case of sulfuric acid, in case of humic acid also we are getting fibrous structures, and in the combination of high concentration and low electrolyte concentration, we are getting spherical structures, and also in case of pH, at different pH conditions like 6.5, 7, 8 and 9.5, we are getting also spherical and rigid structures. So, this is how, depending on the concentration of the sample as well as the electrolyte concentration and pH, the structure of different humic acid and fulvic acid molecule changes. Now, in the most moist soil solutions and fresh water, when humic acids and salt concentration are low, humic acid and fulvic acid should occur as flexible linear polyelectrolytes. That means, what we have seen, that moist soils with the fresh water where humic acid and salt concentrations are low. So, humic acids and salt concentration were low. That means, in this scenario, and both humic acid and fulvic acid, both of these are showing the flexible linear polyelectrolytes. So, this is how the polyelectrolyte or macromolecular structures of soil organic matter changes due to the variation of these determinant variables. So, 1999, another scientist group led by Mainini. So, Mainini et al. Studied the structure of humus as a function of humus origin, pH, ionic strength and mineralogy using spectromicroscopy, and they have also given different structural patterns. So, in dilute acidic high ionic strength condition, like for sodium chloride, high ionic strength, that means high concentration of the electrolyte. So, and dilute acidic solution. So, then humus formed the globular aggregates and ring like structures, as you can see here, and as the fulvic acid concentration increased, so it was the lower concentration. So, as the fulvic acid concentration increased, large sheet like structure, as you can see in this picture, appeared and encapsulated smaller structures, and coiling was not prevalent, and humus dispersed into the small aggregates less than 0.1 micron in solutions of pH greater than 8. So, as you can see that how this solution, how this structure is changing based on the pH as well as the concentration of humic acid as well as fulvic acid fractions. So, in concentrated humus solutions form globular aggregates bound together with thin films of humic substances. Now, in these two pictures you can see, in dilute fulvic acid solutions of calcium, copper and iron, fulvic acid form thread and net like structures, as you can see thread and net like structures. As fulvic acid cation concentration increases, the structures were larger and form rigid sheets. So, this is the another group of scientists, they have shown different structures of humic acid and fulvic acid and how they change for different concentration of different concentration of humic acid, fulvic acid, as well as their and also due to the presence of certain cations. Another scientist group called this Namjesnik and Dejanovich and Morris in 2010 studies soil organic matter structures in hematite and mica. So, they have found that soil organic matter can be bound to hematite and mica, and in mica the intermediate pH and low soil organic matter concentration, large spherical aggregates were obtained, and in case of higher soil organic matter concentration, ring like structures with considerable porosity was observed. On the other hand, in case of hematite with iron concentration, iron present and a pH of 4, globular structure with mean diameter of 0.3 micrometer was observed. So, you can see lots of different structural research have been executed so far, and scientists have produced lots of information of their macromolecular structures. Now, we have to see the functional groups and charge characteristics of soil organic matter. Remember that soil organic matter has a higher surface area and CEC than clay minerals. We have already discussed it in details, because soil organic matter has a huge number of different functional groups which get which dissociate, which basically dissociates due to the change of pH, and as a result there is a huge amount of negative charge. Now, remember, it contributes 80% of the total CEC of the soil. It is a huge. So, that is why soil organic matter is considered one of the major fraction that controls the soil chemical properties. Now, organic matter is a variable charge component. Obviously, like as soil clay mineral, there is no crystalline structure, defined crystalline structure where isomorphous substitution can occur. So, due to the absence of isomorphous substitution, all the negative charge whatever we see on the surface of the negative on the organic matter basically due to the negative charge which produced due to the variable charge component. So, that is why organic matter is a variable charge component. This charge depends on the surrounding pH condition. Now, there is a concept called point of zero charge or PZC. That means the pH at which colloidal particles has no net charge. Due to the presence of variable charge or pH dependent charge, there may be possibility of producing of either positive charge or negative charge, although negative charge is prevalent. However, there will be one pH at which all the positive and negative charge will counterbalance each other and the net charge will be 0. So, that point of pH is known as point of zero charge. So, point of zero charge of soil organic matter is basically comes around pH 3. So, soil organic matter is basically negatively charged as value greater than pH 3. So, if it is pH less than pH 3, then soil organic matter will produce the positive charge. However, at pH greater than 3, it will produce the dissociated functional groups. As a result of that, they will produce the negative charge. Remember that as pH increases, the degree of negative charge increases due to the deprotonation or dissociation of H plus from the functional groups. We have already seen that as the pH increases, the deprotonation occurs from the carboxylic group, from the phenolic group which are present in the organic matter, and as a result the negative charge increases, and as the negative charge increases also the cation capacity increases. So, functional groups and charge characteristics of soil organic matter, if you see, major acidic functional groups are carboxyl, then quinones, then phenolic hydroxyl groups and enols. As you can see, carboxyl, quinone, then phenolic hydroxyl, then enol. These are the major acidic functional groups which are present in soil organic matter. Now, remember that as we have already discussed this structure in our previous lecture. So, remember that the carboxyl and phenolic groups are, this is the carboxyl group as we can see, and this is the phenolic group. So, both these groups basically deprotonated at pH common in most soils. So, you can see this is the deprotonated carboxyl group and this is a deprotonated phenolic group. So, at the normal pH condition they get deprotonated. So, they are major contributors of the negative charge in the soil. So, that is why when the organic matter is higher in case of any soil, that will have higher cationation capacity, and as a result obviously that soil is considered as more nutrient rich because they can attract that positive charge cations. Now, carboxyl group, remember, contributes 55% of the total cationation capacity of the soil organic matter. However, phenolic hydroxyl groups, enols and quinonic groups produces around 30% of the CEC of the soil organic matter up to pH 7. So, this is very important. So, we can see that carboxyl groups and phenolic groups, a carboxyl group is the major producer of the negative charge or CEC and followed by phenol and other groups. So if we consider the contribution of soil organic matter and soil C, contribution of soil organic matter in soil C, this chart gives us some overview. So we can see here at pH increases from 2.5 to 8 in this direction, clay fraction increases and also organic matter fraction increases. Now one thing you see that the CEC this is basically the CEC due to the clay fraction and this is basically CEC due to the organic matter fraction. So one thing is clear that with increase in soil pH as we are going in this direction, the CEC of the clay changes much less than that of CEC of soil organic matter. So soil organic matter is the better contributor of CEC as compared to the clay, and this is basically due to the presence of permanent charges in the clay which changes little with pH. So in case of soil, maximum charge except from kaolinite and amorphous iron aluminum oxides, most of the charge which is developed in case of crystalline clay minerals are due to permanent charge which changes very little with the pH. However, in case of soil organic matter, all the charges are basically pH dependent charge or variable charge. So you can see with the changes of the pH, the magnitude of increase of CEC is higher in case of organic matter as compared to the soil. So however, CEC of organic matter fraction increases drastically with increase in pH due to the dissolution of H plus and their functional groups which you have already seen. Now soil organic matter also drastically increase the CEC of the sandy soil. So that is why in case of sandy soil, one of the way to increase its fertility is to apply organic matter. So we can restore the CEC. That means we are basically applying soil organic matter into the sandy soil which are basically electrically neutral to increase the soil organic matter concentration, and as a result the negative charge increases in the soil organic, as a result the negative charge increases attracting more plant available nutrients or cationic nutrients. Now, if you see the contribution of soil organic matter to soil buffering capacity, one thing is clear, this graph shows us that pH versus a base. So here there are two graphs and we can see A is basically the peat humic acid and B is basically the soil humic acid. So two fractions we can see. So basically if we add the base, if we continue to add base, how their pH changes, they will basically produce this type of pattern, and soil organic, and this pattern is basically we are getting due to the buffering capacity of the soil organic matter. Remember, soil organic matter is a major contributor to the buffering capacity of the soil. A typical titration curve we are seeing here by adding the base into the organic matter which is inherently somewhat acidic in nature. So we are seeing here three zones, zone 1, zone 2 and zone 3. So in case of zone 1, most acidic region, we can see it is called the most acidic region where dissociation of the carboxyl groups are happening. In the zone 2, intermediate range attribute, basically it is an intermediate range which is attributed to the combination of dissociation of weak carboxyl groups and very weak acid groups. However, in zone 3, we are seeing the dissociation of phenolic hydroxyl and other very weak acid groups. So you can see this is the basically titration curve showing and this slope shows the buffering capacity of the soil organic matter and dividing the area into three zones by dissociation, by dissociation of different groups which are present or functional groups which are present in soil organic matter. Now soil organic matter generally has weak acid characteristics, that is why it has some buffering capacity, and this is due to the complex of soil organic matter with metals like aluminum, then ferric, Cu2 plus etc. And hence the important functional groups like carboxyl and they are mostly occurs at complex with metals producing the chelates. So if we see that the humic substances and metal interactions, soil organic matter complexes with various metal ions, and basically we will see that these affects the retention and mobility of metal contaminants in soil and water, and the affinities of various functional groups towards metal ions are as follows. Basically, the highest affinity can be seen in case of enolate, followed by amine, then azo compound, then green nitrogen compound, followed by carboxylate, then ether, then carbonyl. So, the humic substance also vary in their affinity to produce the metal complex, and their affinity towards the metal ion also varies from one functional group to another functional group, as we can see here. Now, humic substance metal interaction, if we want to see that, the interaction of between the soil organic matter and humus and soil organic metal and metal in case of water body can be described by this picture. You can see here. Now, there are three types of interaction you can see. One is the reaction between dissolved oxygen, dissolved organic carbon and metal ions. As you can see, this is the dissolved phase, where we can see that humic substances are interacting with copper here, and reaction between the suspended organic carbon and metal ions. So, this is the suspended organic carbon and suspended organic carbon and metal ions. You can see here, this is the metal ion and suspended sediments basically, which is, and this organic matter is basically coated in the sand grain and getting suspended, and the finally is the reaction between the bottom sediments and the metal ions, as you can see here, where basically the DOC is the organic carbon which passes through the 0.545 micrometer silver filter, and SOC is the organic carbon which is retained on the 0.45 micrometer silver filter. So, this is the difference. So, in case of water body, we can see these different types of humic substance and metal interaction in three different phases. So, total binding capacity of, in case of total binding capacity of humic acid for metal is varies from 200 to 600 micromole per gram, whereas 33% of these due to retention of cation complexing site, and carboxyl and phenolic groups are the major complexing sites. And when two or more organic functional groups coordinate the metal ion to form a ring-like structure, a form of complexation occurs known as chelation. So, you can see here there chelation of metal by organic compounds, where it is the salicylic acid, it is chelating the copper, phthalic acid, it is chelating the copper, picolinic acid is also chelating the copper, oxalic acid chelating the copper. So, different organic compounds, how they are coordinating with the metal ion to form a ring like structure, and remember that it is always two or more organic functional groups. Okay. So, this is how this chelates occurs. So, friend, let us wrap up here this lecture, and in the next lecture we will be discussing more about this chelation process and how this chelates affects the movement and availability of different metals. So, let us wrap up this lecture here, and in the next lecture we will be discussing these in details. Thank you very much.